Okay, so this is going to be your, if you got these notes in class, this will be your follow-up, your extra set of review, I guess you could say. And if we didn't make it through the whole thing in class, which I didn't for most of you guys, and that's okay, that's why I'm making this, then this will serve as your source of notes for either mechanical advantage or your conservation of energy, whichever one we didn't get to. Now, I didn't include Chapter 10, Section 2 in your reading note quiz that was due the other day, because I thought the book made this way too complicated. They provided equations for more machines than we're actually going to talk about in class or that we have time to deal with. So I've narrowed it down, and these are the essentials. This is what you need. We have to start with by remembering literally the work energy theorem, that changing the energy of a system requires us to do work on that system. Now, as a species, that's typically going to mean moving things that are heavier than we can move, which is good for building or growing crops or whatever it is that we have learned to do, making tools, things like that. And that's literally what has separated us primarily from the vast majority of other species on the planet, is our ability to use these machines. I'm not talking about cell phones and cars or satellites and GPS systems. I'm talking about our very, very most simple machines, levers and pulleys and gears and those sorts of guys, right? Even the wheel is a good example of this, and I'll list those examples here in a second. Machines improve our ability to do work. They improve our ability to change the energy of a system. They don't do this by, sorry for the bell, they don't do this by manipulating how much work is done, and that's something I'm going to come back to in a second, but they do this by changing either the magnitude of the amount of force that we apply to that machine. Magnitude, remember, was one of our first vocab terms of the year. It literally just means amount. Don't be scared by it, please. Right? So it's changing either the amount of force required or the amount of force you get out of that machine, or it changes the direction that force is being applied. A good example of changing direction is a pulley. You pull down on the rope to lift something up. And changing that direction is oftentimes enough to literally just make the load easier to bear. And so this part right down here, this is the test question. This is the reason I left this as a blank. The work you put into a machine does not change. The amount of work you put into the machine is the exact amount of work you get out of the machine, because work is the amount that the energy of the system changes by. And we can't create or destroy energy. Neither of us are God. It's not something that we can do. The amount of energy that you put into the machine is the same amount of energy that you're going to get back out of the machine. What it does do is allow you to apply your force in a different direction or over a different distance to get more force out of that machine, usually over a shorter direction, right? You apply less force over a larger distance, and the machine gives you more force out of a smaller distance. A really good example of this is a lever. So if you've got a very large, heavy item that you're trying to move, in class I actually used an example from the most recent Avengers movie because it works really well. But the really heavy item on one side of that lever that you're trying to move would normally require a tremendous amount of force on your part if you wanted to lift it. But if you put the fulcrum, the pivot point for your lever, nearer the heavy object that you're trying to lift, and you apply a small force, I'm going to make this a lowercase f, a small force over a very large distance, right? That would be your work, a small force over a very large distance. You'll be able to move a very large amount of force, a very large amount of weight, because force is just weight, is just a force of gravity, over a very short distance. And that's what machines are able to do for us, right? Even if it's not a lever. Another good example of this would be a ramp. The purpose of a ramp is to physically increase your potential energy by a certain amount, right? You step up over it, most of us do. But if you're in a wheelchair and you cannot step up over the front porch of a home or whatever it is, you've got two options. Either have a couple of people come out and help pick you up over that front porch or that front stoop, whatever you want to call it, or apply less force over a much longer distance, right? You can either travel up that vertical distance and get to your new potential energy vertically, which requires a lot of effort, and in a wheelchair you can't do that by yourself, or on your own travel across the hypotenuse of this triangle to achieve your new potential energy. Longer distance, less force because you can do it on your own. and you're able to achieve the same change in energy. You're able to get the same work done. That is what and this is literally what we call them, simple machines do for us. Examples of simple machines, I've already listed 2 of them. The first one being a lever. You can think of this as a seesaw, a lever. A seesaw on a playground where the fulcrum, the pivot, is right in the middle of the seesaw is actually a really, really bad lever, where the distance on both sides, distance away from the center, distance away from that pivot, are equal, is not very advantageous for us. It doesn't amplify the amount of force that we could apply to something. But the minute you start moving that fulcrum, that pivot from one side to the other, that's where you're able to start getting the exchange of, I'm going to move this side further and this side will be able to lift more. The other side will be able to lift more. So that's a lever. The next one obviously was a ramp. Another one that we will talk about and calculate a little bit with in assignment 4 is a pulley. So those are the 3 that we're going to deal with. Now we're not going to do the whole, the number of times you loop the rope around is going to give you a 2 times or 3 times or 4 times mechanical advantage. We'll talk about it briefly, but we're just going to talk about pulleys in terms of efficiency, and I'll get to that in a second. Things we won't calculate in class just because the calculations and identifying variables for these can get a little bit messy are going to be things like gears. You probably didn't think about gears as being a simple machine, but you definitely think about it when you start trying to pedal uphill and you frantically start shifting gears on your bike trying to find something that isn't awful to try and pedal with. Going right along with gears, even though it is literally one of the simplest machines out there, is the wheel and axle. Just because it deals very, very, very closely with the same ideas as the gears and the ratios at which the diameters are for each one of those objects and how quickly they rotate compared to one another and things that we're not going to get into. The book does go over all of the gear ratio calculations, and I think identifying those variables is a little bit too tricky for what we need to accomplish in this class. And then the last one is a wedge. Wedge is, you can think of like a hatchet or an axe or a knife in general. A pair of scissors would be an example of a wedge. Those sorts of machines are pretty helpful, but not part of the calculations that I want us doing. So those are our simple machines that we've got in the class. The 3 on the left are the ones we're going to be doing calculations with. Because this is physics, of course we can do this. We can calculate how helpful these machines are. And because physicists are really unoriginal when it comes to naming things, we literally call this mechanical advantage. This is a ratio of the forces at play, literally the amount of force you put into the machine versus the amount of force the machine gives you or puts out for you. The object that you're moving is always going to be labeled as the resistance. It is the thing resisting the motion of the machine. That's how I like to think of it. And the effort is always going to be the thing that you are putting into the machine. So in this case, it is the amount of force that you put into the machine, how strong you have to pull on the rope, or the amount of force you have to put into moving across the ramp or climbing the rope, if you want to talk about the advantages of a ramp, that sort of thing. In this particular case, notice that it's a force divided by a force, so you do not have units. No units. That's kind of important. I didn't mention that in class yet. I was waiting until we started doing the homework for it. So if you're watching this, the 10 or 12 of you who do, you're welcome. Anyways, so it's just a ratio. That's all it is, how advantageous it is. What the machine does for you divided by what you put into it. Ideally, that should be greater than 1. Now, also ideally, all of the energy that you put into this is transferred from one object to another. We don't live in an ideal world. That guy right there is always present. We can't get rid of it. I'm in the camp of people, physicists, who don't think you could ever get rid of it, actually, interestingly enough. And I can explain that when we get to electrostatics and subatomic particles. But because this does not include or eliminate, friction. This is our very real world example of what that machine would actually do for you. There's another way we can calculate mechanical advantage that is more hypothetical, and literally we call it the ideal mechanical advantage, because again, we're not very original. So ideal mechanical advantage, at least when it comes to naming things, is a ratio of distances. And this is beneficial because this tells you what the machine should be able to do for you. The ideal mechanical advantage is what the machine should do for you. Mechanical advantage is what it actually does in the real world with friction included, or friction considered, I guess you should say. If you would like to know where this equation came from, the proof is in the book. They spend an entire page going over this in chapter 10, section 2. I'm not going to do it with you because I always lose you guys when I do that. But I do want you to notice that that fraction has flipped. Mechanical advantage and ideal mechanical advantage have effort and resistance in opposite ends or opposite sides of that fraction bar. Mechanical advantage is resistance over effort. Ideal mechanical advantage is effort over resistance. Again, the proof is in the book. You could see mathematically how they flip and why they flip. But I just wanted you to know it's not always one over the other. They write them down, basically, I guess is the point. Effort is still the thing you do, the thing you put in, the physical distance you move. So this would be the distance you move horizontally, or not horizontally, at an angle across the hypotenuse of a ramp. The resistant would be the objective of the ramp, to get you up to that new potential energy, that new height, so that you would have a new amount of potential energy. That would be your resistant distance, is the height of the ramp. Oh man, I got all sorts of messed up. Cool, I love technology. Anyways, I'm going to continue on. So, because friction exists, no machine is ever going to be perfect. Can't get rid of friction. I don't think we'll ever be able to get rid of it. There are lots of engineers out there trying to get rid of it. But basically that means that we can calculate this guy called efficiency. Efficiency is going to be mechanical advantage divided by ideal mechanical advantage, or the work you get out of the machine divided by the work you get into the machine, right? You're going to lose some energy. You're going to lose some work because of friction. Either it generates heat, or it generates sound, or potentially light, a little less common, but it could. So in this particular case, you're never going to have an efficiency over 100%. That's a really good test-taking tip. If you go to calculate efficiency in a homework assignment or on an exam and you get 120%, one of two things has happened. You have figured out how to completely eliminate friction. You should publish your work, get your Nobel Prize, revolutionize the world. I'd like a tour of NASA when they inevitably recruit you. All right? I'll be in the stands cheering you on, basically. The other more likely scenario is that you just have to flip your fraction. Right? It should always be the work you get out of the machine divided by the work you put in, and the work you get out should always be less. Mechanical advantage should always be less than IMA. So that's just something to keep in mind, right? Little test-taking tip. Now, conservation of energy. This is chapter 11. This is what your reading note quiz for Thursday is all about. So, just like chemistry last year or momentum from literally the last unit, those have been little white lies. I don't want to say, it's not like we intentionally lied to you to be malicious. We just didn't give you the whole story. There is only one conservation law that holds true, and we don't call it a law because it's something that we wrote down and we want the universe to follow. This is an observation. There's only one thing in the universe that we have ever truly noticed gets conserved, and that is energy, right? Mass can be destroyed. Heck, mass can be created. It's kind of what's happening in the Big Bang. Took pure energy, turned it into mass through processes that we're just now starting to try and understand. Nuclear fission, the stuff that happens inside a nuclear reactor or inside of a nuclear bomb, has always had a exchange of mass into pure energy. It's how we get the energy out of that mass, right? The pieces that it falls apart into don't add up to the total that you started with, and the missing mass is our energy that we use to power our lights right now. Even momentum. You're going to lose some momentum in a collision, not because momentum just ceased to exist and disappeared, but because we hadn't talked about kinetic energy yet. And that kinetic energy gets converted from motion to sound. Everyone's heard a car crash. Oftentimes, that's the first thing that tells you cars crashed, was the sound that they produce. The bending metal is going to produce a lot of heat. All of those different versions of kinetic energy come out of the loss in velocity. So, those are conservation of mass, conservation of momentum, not entirely lies, more so simplified, very specific examples. They don't encompass the whole truth, and energy does, right? Physicists are basically accountants. We have never observed energy go missing or energy appear from nowhere. We can track where all of it came from. Now, where did it all initially come from? We have no idea. There's not an answer for that question yet. We can trace it all back to the Big Bang. What happened before that, no one's got a clue. But all energy since then that objects have, they received from somewhere, and all energy that an object loses is transferred to something else. And that's the point of the lab that we're doing on Tuesday and Wednesday in class. The total energy of the system, kinetic and potential, never changes, this number. And this is what we'll be calculating in class, and you'll be able to see. Now, we'll be rounding some numbers here and there, so we might get some fluctuation, but they'll all be right at the same level, the same amount of energy. The last bit of this is a really, really good example of a drop problem. And we're not going to do throw-up problems or projectile at angle sort of problems with energy. We totally could, but this isn't an honors class, so we're not going to do it. What I did want to do with you guys here, though, is walk you through it so you have an example of conservation of energy similar to the roller coaster lab and similar to the problems that I'll be asking you on the test, right? We're going to go back to our good old-fashioned drop problems. For all drop problems, the initial velocity was always 0, and that means that you start with absolutely no kinetic energy, and 0 joules is our value for kinetic energy there at the beginning. The amount of potential energy that we have is our 10 Newton weight for that object. Remember, weight is mass and gravity. So this is our conversation the last time we were together. So I've just simplified that. I could do 1 kilogram multiplied by 10 meters per second, but squared, but I still get 10. Multiplied by a height of 2 meters. And so I'm going to get 20 joules of energy. When you add those together, they're going to equal your total energy for the entire system. All of the energy for a drop problem comes from potential energy before the object gets moving. That's all that needed to be. Now, I'm not going to ask you to calculate velocities after it's fallen a certain distance. That was first semester stuff. This is the equation I used. If you would like to practice it and verify it, make sure I'm not lying to you, go for it. It's all right there. If you want me to walk you through it individually, I will happily do so. The velocity an object is going to have after it's fallen 1 meter is 4.47 meters per second. Right? I put 1 in for my distance, multiplied by 10, multiplied by 2, 0 is my initial velocity, and then I took the square root. Now, we're going to take that velocity, which I would give you in class or on an exam, 4.47, and you're going to square it. Multiply it by the object's mass, not its weight. I use the weight up top for potential energy. We have to use mass for kinetic energy. Again, divide by 10, just like we talked about last time we were together. So you square that value for your velocity, multiply by literally 0.5, and you're going to get roughly 10 joules of kinetic energy. That is exactly half the energy you had before. We have traveled halfway down towards the ground. That's not a coincidence. Your new potential energy at a height of 1 meter, because remember, you're not 2 meters off the ground anymore, is still your object's weight of 10 newtons multiplied by its new height above the ground, 1 meter, and you get 10. Last time I checked, 10 plus 10 is still 20. So your total energy has not changed. And in the lab that we're going to be doing for the roller coaster, it's not going to change. Rounding, sure, we might get, 5 versus 4.99 versus 5.01, but it's going to be 5, just depending on how we round this, because we can't keep every digit and every decimal that we're going to get. There's going to be a lot of them, trust me. So 6.32 is the velocity you're going to get just before this hits the ground. Again, 2 meters is the distance the object fell. The initial velocity was 0. You can use that calculation if you would like to confirm my numbers. Your velocity here of 6.32, mass of still 1, is going to give you a number of 20 joules. Your new height above the ground is 0. You have landed on the ground. Your weight is still 10 newtons, but your height is 0. Gravity has no ability to move that object anymore, therefore it has no potential. And your 20 and 0 are going to give you 20. This is what we'll notice in every single drop problem. Total energy is conserved. At the beginning, it's all potential. At the bottom, it's all kinetic. Halfway through, it's half kinetic, half potential, but it still adds up to be the same number. These are the 5 crucial things that you can always remember. So if you're doing a drop problem on the homework, the review guide, practice quizzes, whatever it is I've given you, these are the 5 things you should come back to if you get stumped. Total energy never changes. Meaning if you can find kinetic energy at the bottom or potential energy at the top, you know the total energy all the way down. Always going to be true. Kinetic energy clearly increased as we fell, right? Because velocity also increased. Potential energy decreased as you fell because your height above the ground decreased. Kinetic energy at the top of an object's motion is always 0, and potential energy at the bottom of an object's motion is also always 0. Those 5 things are always true for a drop problem. I mean, honestly, throw a problem, projectile, and angle problem. Doesn't matter. It's just true of energy. But that was it. Those were the notes. I didn't get to the last problem on the backside with some of you guys, so I wanted to make sure you had a place where you could find all of that. Assignment 4 deals with the first 5 questions are work, power, and energy from assignment 2, and the last 5 questions are all your mechanical advantage and efficiency stuff. So if you've got questions on those, don't hesitate to ask. It's not due till Friday, so you've got plenty of time. Just make sure you're actually asking questions if you have them. That's about it. I will see you guys later.